Hello friends. So today we are going to see the second type of, in this video we are going to see the second type of optical source which is used in fiber optic communication system, which is laser. Now as you see in this particular figure, it gives a LED versus laser spectral width diagram where you can easily compare between laser spectral width and LED spectral width. If you see, the laser spectral width is very much greater compared to your laser spectral width. So this is one of the reasons why laser is preferred over LED for single mode fibers, whereas LED are specially used in case of multi-mode fibers. And one more reason is that, as we know, multi-mode fiber core has a larger core diameter compared to the single mode core diameter. So as discussed in the previous lectures, what is the structure of LED, or what is its advantage, what is its disadvantage. We'll now see what this laser as an optical source has to say. So in the previous lectures we have discussed such as some basic principles there, wherein this optical sources, when they are optical sources are basically made, or the material which is used in these sources are basically semiconductor materials, and the laser also is basically which is used for optical fiber communication, is made up of semiconductor material. So what is laser? Laser is nothing but light amplification by stimulated emission and radiation. So what are its advantages is that it provides a radiation which is spatial and temporal coherence, and also it is the radiation output from a laser is highly monochromatic and the light beam is very directional. So how does it happen? Although there are different types of lasers wherein these lasers are used for different applications, the basic principle of working of a laser remains same. That is based on these three principles: absorption, spontaneous emission, and stimulated emission. Now these three processes can be explained by taking a two-level energy diagram. So you have two states over here, E1 and E2. One is a lower state, one is a higher state. So what does these three processes can be explained by considering the Planck's law. Now what it says is absorption or emission of a photon of energy h nu 12 is given by E2 minus E1. So normally the system is in ground state. When a photon of energy h nu 12 impinges on the system, an electron in state E1 can absorb the photon energy and be excited to state E2, as shown in this particular figure. Now since this is an unstable state, what happens is the electron will shortly return to ground state, thereby emitting a photon of energy h nu 12. So when this happens, this process is called as spontaneous emission, because you don't have any external stimulation which is happening over here, due to which the electron from the unstable state coming to the lower state. Now this thing can also happen by giving a external stimulation, which you see in this third figure, which is called as a stimulated emission. Now how does it happen is, If a photon of energy h mu12 impinges on the system while electron is still in its excited state, the electron is immediately stimulated to drop to the ground state and give off a photon of energy h nu12. The emitted photon is in phase with the incident photon, and the resultant emission is known as the stimulated emission. Because of this process, this release of energy results in a coherent release of energy because both the photons which are released are in phase. The one which has stimulated the emission and the one which is released are both in phase. So if you see in this figure, this is nothing but explaining the stimulated emission, wherein if you see these two photons, they are in phase. So in stimulated emission, incident and stimulated photons will have identical energy, identical wavelength, due to which there will be narrow line width, identical direction leading to narrow beam width, identical phase leading to coherence, identical polarization. Now, as you see in this figure again, it's explaining these three processes: what happens before, what happens after. In case of stimulated emission, if you see, there is production of more photons over here. So in thermal equilibrium, if you see, the density of excited electrons is very small. So most of the photons incident on the system will therefore be absorbed. So that stimulated emission is essentially negligible. Stimulated emission will exceed absorption only if the population of the excited states is greater than that of ground state. This condition is known as the population inversion. Now, since that is not a equilibrium stage, what is going to happen is there will be more number of unstable electrons in a higher stage, which will try to come to the stable state by emitting photons. So, in a semiconductor laser, a population inversion is must for lasing action or for maximum amplification of light. So for population inversion to take place, it is injected by electrons. You inject electrons into the material at the device contacts to fill the lower energy states of the conduction band. And this is done by a process called as pumping. So a very important condition for the stimulated emission to happen in a laser is that the state has to change from, or it should not be in its thermal equilibrium state, wherein in thermal equilibrium stage you have more, you don't have sufficient number of electrons in the higher state, so you can't have emission of photons. So if I have to summarize, you see in this particular first diagram over here, the pump on, so atoms are excited in the high energy state, so due to which there is spontaneous emission. As more photons are released, they collide with each other, which leads to multiplication of photons. And mind you, this photons will be in phase. All of these photons will be in stage. So as the amplification is taking place, the multiplication of photons is taking place, one eventually a state is reached which is called a steady state laser operation. The state during which optical output will be released through this reflector. Now, this is nothing but a optical resonator cavity wherein the lasing action will take place. So, based on the resonator cavity, you have two types of laser diodes. First one is the Fabry-Perot resonator cavity, wherein you have structure similar like this, wherein you will have mirrors, partially reflecting mirrors, in which there will be a resonator cavity. The optical amplification will take place inside this cavity. In the second case, it's distributed feedback laser diode, wherein the amplification basically takes place due to the difference. If you see in this figure, it's a Fabry-Perot laser diode. You have partially reflecting surfaces. And in the second case, if you see, this lasing or the optical amplification happens mainly due to the change in the refractive index in the structure, which is provided by this fiber Bragg gratings. So if you see, based on the type of amplification, based on the type of resonator cavity, you have two types of laser, Fabry-Perot laser cavity, and the second type is your distributed feedback laser diode. So if we have to summarize the contents, what we have seen is what is the basic principle of laser operation, which is absorption, spontaneous emission, stimulated emission. And for stimulated emission to happen, the important condition is that there should be population inversion. Only when population inversion is attained, then only you can have the stimulated emissions happening. So we'll see these two particular type of laser, what is the structure, how both the laser diodes are different, and how does optical amplification takes place inside Fabry-Perot resonator cavity, how it happens in distributed feedback laser diode in the next video. So hope you have understood the basic principle of laser diode. Go ahead and answer the quizzes which are provided in the next section in Moodle. Thank you.